Okay, so yesterday we talked about single replacement reactions where you have a metal and a salt. And if the metal on the activity chart is higher than the salt, you have a reaction where the metal becomes an ion and the ion becomes a metal. Today we're going to have two ions, two mixtures. So we have two mixtures. An aqueous solution of, aqueous again means it's mixed in water, AQ. So we're taking an AQ mixture of silver nitrate and dumping it into an AQ mixture of sodium chloride. So now we have the opportunity for the ions to pair up with a different set. So now the silver can pair up with the chlorine, where before they were separate. Now, when you get this pairing up, you have a situation. The reason why the silver over here, the reason why you have the silver and nitrate in a clear colorless solution is because we have a solvating force of the water that's keeping them apart. So whenever you mix anything like sugar and water, you mix it up and becomes, the white sugar becomes invisible. Salt, table salt, put it in water, mix it up. The white table salt becomes colorless and clear. Those are called solutions. Now we're going to go delve into this very deeply in Unit 5. But until then, you need to understand that sometimes when two ions, a cation and an anion, come together, they do one of two things. They form a solid or they stay separated. Now, sometimes you have something called partial solubility. Those are kind of the exceptions. But in this class, we're talking about either they form a solid or not, nothing in between. Okay, so we're going to put silver nitrate, and it's nice and clear, so we know that they're separate. Bashing heads are not allowed. We have sodium chloride mixed in water, also not forming a solid. When we mix these two together, though, we have a new possible combination. We have the silver now can hook up with the chlorine, and the sodium can hook up with the NO3 nitrate. Now the question is, do they form solids? New combination. So what you need are one of two things. And when you take your next chemistry class, you're going to have to memorize these rules. Now in this class, you can either memorize the rules or use my handout. My handout is very visual, I should say. It's also visible. This is going to be black and white. What you do is you take the anion with your finger, cation with your other finger, and see where they cross. If they cross and it's black, that means you form a solid. If it's white, it doesn't form anything. Now, this was based on the rules below. And in my opinion, the rules are something you need to know eventually when you get into a higher chemistry class. In this class, we're using this, and you'll have this on your next test on Saturday. And your next test is a week from today. Look at your practice tests, like I always give you, and it'll be similar to that. Okay, so anion, cation, where they cross is where their solid's going to form. Black is solid, white is not, no soluble. Okay. Now, why would silver chloride form a solid and sodium nitrate below it won't form a solid? Okay, you've got two forces fighting. See who's stronger. We have solvating force and we've got crystal lattice force. Keeping it together. What's stronger? If the solvating force is stronger, you won't form a solid. If the crystal lattice force is stronger, you form a solid. Now, if they're equal, then you get something called partially soluble, which means it forms a mushy solid. But in our class, it's going to form one or the other. And this table is based upon these rules below. Now, let's look at this table more closely. Notice we have chloride and silver. And when they cross, it's black. That means when you add silver ion and a chloride ion together, you'll get a white solid. Now, that's a classic test for chloride present. Now, back in the 20s and 30s, if you were a CSI, you did wet chemistry. They don't do that much anymore because they use instruments instead. But back in the 20s and 30s, you were mixing stuff together. And one of the classic tests for presence of chloride was you add silver to the solution. You get a white solid, bam, positive test for chloride. Or bromine or iodine. So any of the halogens will give you a positive test with silver. So then you need to further do another couple wet tests. Okay, let's look at sodium now. Sodium nitrate. Okay, where those cross, it's white. Yeah. Yep. Yep. Exactly. And unfortunately, lead chloride and silver chloride look exactly the same. They're both white solids. So, but yeah, anytime there's black, solid. And if you go down to the rules below, it'll say that, and all this stuff. Before you sit down, grab a hand up. Okay, so does this make sense, this chart? Took me a long time to make this thing, but anyway, it's a nice chart. I've been using this for a long time. Okay. Thank you. Okay, so again, I want to emphasize we have two kinds of reactions we're studying this weekend. Single replacement, you have to have a metal or an acid plus salt. That's called single replacement. That's an oxidative reduction reaction. Double replacement is you have a salt and a salt solution. Add those together. And there's no oxidation reduction. So this has got they abbreviate that redox. And the double replacement reaction is there's no oxidation reduction, only single replacement. And the metal is what's being oxidized and reduced. So if we look at the equation of what we just did, adding the silver nitrate solution AQ to the sodium chloride solution AQ, we get a new combination. And once we look on the chart, we can figure out whether it's going to be an S or an AQ. So white is AQ, black is S. And then we have to make sure it's balanced. So we have one sodium, one silver, one chloride, one chloride. So it's balanced as written, but always check. Always check, do a quick inventory. Now, you're going to be asked to write 3 kinds of equations for double replacement reactions. The top one, we have everything is together. That's called the molecular equation, or the ME. Down below, I've separated out the different ions. That's called the total ionic equation, or TIE. Now, if something happens, in other words, if we have a solid form, then we have to write yet another equation, and that's called the net ionic equation. And all you do is you put the ions together that form the solid. Silver plus chloride equals silver chloride, solid. Now, in your lab next week, you're going to be writing these equations. Okay? I want you to not write the total ionic equation, though. You're going to do that in your next class. But for us, we're doing first the molecular equation, and if there's a reaction, a solid form, then you're going to write out the net ionic equation. Then you're also going to list the spectator ions. What did not react? Well, the sodium, the nitrate didn't form a solid. So those are spectator ions. Okay, sometimes when you add 2 solutions together, like potassium chloride, aqueous, plus sodium sulfide, aqueous. Now we know that's a double replacement because it's a salt and a salt. So when we write the molecular equation, it's going to be KCl plus Na2S. The reason why it's a 2 is because sulfur is a -2 on your common ion chart. Sodium is a +1, so we need 2 sodiums to balance the sulfur. Okay, that yields Ks plus 2 sodium chlorides. So that's the molecular equation. Then you balance it, or you check for balance, making sure it's balanced. Okay, so is there a net ionic equation? Well, we need your solubility chart to find out. So what we're going to do is we're going to put the K and the S together. Look on your chart. Okay, you're going to have a side and a top, bring them together. What color square is it? White. So no solid. So this becomes aqueous. Sodium chloride, what color square is that? Use your fingers. What color is the square? White. So no solid also. So basically, when we dump these two solutions together, it appears like nothing happens. So the solvating force is predominant over the crystal lattice forces. So nothing appears to happen. So the net ionic equation is null set. There is no net ionic equation. You still have to put down, there's no net ionic equation. So that's a typical double replacement problem. I give you two solutions, dump them together, you get the new combination, and see if the new combination forms a solid or not. If it does, then you need to write the net ionic equation and make sure you balance everything. So in some ways, I think the double replacement is easier than the single replacement. So next semester, I'm going to swap. I'm going to do double replacement first, then single replacement. Every time I teach this, I always say that. And I've yet to do it. Yeah.
If it's still a liquid, we use the molecular equation of the two molecules.
Well, you're always going to have to do three things, but I'm having you only do two things. The molecular and the net ionic. So if nothing happens, you still have to put out net ionic with a null sign. Or write no net ionic or something like something to that effect. You have to do both of them all the time. If it's solid, you write out what it is. And if they're both white, then you say no net ionic. And you always also have to do spectator ions. So if you have no net ionic equation, that means everything's spectator. Everything is spectator. Why is this so? Okay, so let's do one more. Let's do why is this so light? Okay, so I've got magnesium phosphate, excuse me, sodium phosphate. Notice it's an A3. The sodium is +1. Phosphate is a -3. I'm going to add that to a solution of magnesium nitrate. Nitrate's -1. Magnesium's +2. So we need 2 of these. Okay. So, and those are both aqueous. So when we have the new combination, we're going to end up with okay, so we need to determine there's a solid form. So then we look up magnesium on the top and go down to phosphate on the left. Black. That means that's a solid. And then sodium nitrate again is no solid, so it's aqueous. Okay, so is this balanced? No. We've got 3 sodiums on the left, 1 on the right. We've got 2 nitrates. Let's do a okay, so we have 3 sodiums on the left and the right. PO4, we have 1 on the left, 2 on the right. So if we put magnesiums, we have 1 and 3, nitrates 1 and 3. So that's definitely not balanced. So let's go ahead and balance it now. Okay, phosphates. Okay, we need 2 on the left. So put a 2 here. That makes this 6 sodiums. And we have 3 on the right. So instead of 3, let's make it 6. So now we have 6 sodiums. How many nitrates do we have? Well, we have 6 on the right now. How many nitrates on the left? We have 2. So we need, let's put a 3 here. Now we have 6. Magnesiums, we have 3 and 3. So it's now balanced. And notice I'm keeping the groupings, the NO3 as a group together, as opposed to splitting up the nitrogens and the oxygens. Same with the PO4, because it's on both sides of the equation. So when you're doing this balancing, take advantage of that, because double replacement reactions always have groupings of ions. It's much easier to balance groups rather than individuals. Two phosphates as well on both sides. Okay, so now what about the net ionic equation? Did anything happen? Yes, it did. We formed a solid with the magnesium phosphate. And what are the 2 ions that made up magnesium phosphate? Well, there's a magnesium and the phosphate. Phosphates -3, so we need 2 of those. Magnesium's +2, so we need 3 of those. So that's the net ionic equation. And that's about as hard as it gets. Now, when you get to your next chemistry class, you'll be doing the total ionic. Now, the total ionic aren't that hard, but there's a lot of details you have to do. And that's where you get students frequently mess up, as they understand the whole process is just to get messed up with the details. So that's why I want you to focus on the molecular equation and the net ionic. I want us to get the concept down first and worry about the details later. Okay, so are there any questions about double replacement? Yeah. Huh? I'm going to do a review on Friday. We have a test on Saturday. So there's lots of practice. Okay, this here, net ionic equations is double replacement reactions. And then here are 2 single replacement reaction worksheets. Here's our solubility table. So I've given you lots of practice besides your 2 labs. Now your labs are really good because they give you lots of practice as well. Yeah.
If both become solids, do you need 2 equations or just 1?
Good question. If both of them become solids, you need 2 net ionic equations. So if anything happens, net ionic equation. And if nothing happens, then you write no net ionic equation, or just put null set there. Either way. You always have, and then also write down spectators. Now, if nothing happens, then everything is a spectator. If everything forms solid, then there are no spectators. And you write down no spectator ions. Okay. That's what I wanted to go over today. Double replacement reactions. I guess it's going to be a short lecture today. So your test next week, we're going to review on Friday, but your test next week is going to be single double replacement reactions, balancing equations, looking at finding grams. I give you moles, that kind of stuff. Look at the practice test. It's going to be very similar to that as far as length and the topics covered. Okay, did this make sense?
Fine.
I think this is easier than yesterday. Yeah. Yeah. Test related. Files test related. Hmm?
On the same day we take the.
No, no, you're not turning it on. No. Test 4, you're gonna have a take home more. But not test 3. Yeah.
Wait, emailed you, I think last year, because I'm gonna be out of town next weekend. When can I remake the?
We can do the dry lab for sure. I guess, when are you leaving?
Friday.
Right. I'll just take it when you get back, I guess. What I'll do is I'll post it on Test Related. You can download it, print it, do it, and then give it to me on
So
the next Friday.
we get at home?
Yeah.
Oh, yeah. Oh, that sounds good to me.
Well, I mean,
What else?
where are you going?
Having a pharmacist like conference or something, so taking me with him.
Try to go to the Living Desert. I used to go to my ex-wife's parents lived down there. And it's pretty cool. And you're going the right time of the year too. Won't be.
Yeah,
I went on it. It was like 110 that day.
yeah,
My wife and I, and we fortunately went in the morning. But it's pretty cool though.
yeah.
They lead us a walk. I don't know, probably a couple miles or whatever. And they have little spots where you can stop, little guides and stuff. It's pretty cool.
So we're gonna do that and have some fun in LA too.
Yeah, there's some pretty good restaurants. Go to the what is it called? I'm gonna say Riverwalk, but it's not. It's a shopping center with this now goes through it. Yeah, it's pretty cool.
Thank you.
Sure. Yeah, let me do one thing here. I'm going to stop the video or the recording.